So last time we were working on inverse trigonometric functions, rather the end of it, which is compositions of inverse trigonometric functions. So the first part of these compositions was about combining a function, a trigonometric function and its inverse, and then we finished on an example of an algebraic example where we combine an inverse trigonometric function with some other trig function, not necessarily its inverse. Because otherwise, if this were also a sine, well, just cancel them out, right? However, no, there's a little trick about this. Let's do one more example for tangent of cosine inverse of x. And well, again, we will consider this this quantity right here as our angle theta, and ultimately we will evaluate tangent of some angle theta using SOHCAHTOA information. Well, so from here we can deduce that this is actually theta equals to cosine inverse of x, and well, rewriting this in terms of a trigonometric function, no longer an inverse trigonometric function, this is the same as saying cosine theta equals to x. But hold on, how do we construct a triangle in this case if we just have the quantity x right here? So in the previous example, we have the quotient of the quantities in which, well, sine was the ratio of the opposite over the hypotenuse. Here we don't have like a rational expression. Well, actually, we do have a rational expression because this x can be rewritten as a fraction, that is x over 1. And now it's a rational expression for which, well, in accordance with SOHCAHTOA, this is the opposite. Oh, no, not the opposite. It's the the adjacent. And this is the hypotenuse. With this information, we will construct a right triangle. And, well, let's draw it. This is the reference angle theta, adjacent, which is x, over hypotenuse, which is 1. And we need to find the length of the missing side. That is c squared equals a squared plus b squared. And c squared, that's 1 squared, equals x squared plus b squared. And b squared equals 1 minus x squared, where b will be the square root of 1 minus x squared. That is this length. And now we have all the information required to get this tangent function. And we know that tangent is opposite over adjacent. And the opposite is this radical right here, the square root of 1 minus x squared. And the adjacent is just x. And that's final answer. And then, so what did we do? We were given an expression in terms of trigonometric functions and their inverses, and we use right triangle trigonometry to write an equivalent expression in terms of algebraic expressions, not trigonometric expressions. And again, why do we need to know this? Because, well, later when we get to calculus, when we find derivatives of trigonometric functions and inverse trigonometric functions, we need to go back to these triangular settings. And also when we integrate via the method of trigonometric substitution, which is in Calc 2, we also need to know how to represent these trigonometric functions in terms of algebraic functions. The last topic here, well, so applying inverse trigonometric functions. A yardstick casts 4 feet shadow when the sun is at an angle of elevation theta. They're asking us to find the angle of elevation of the sun to the nearest tenth of a degree. And well, so in this case, they're telling us that a 3 feet pole right here, or a yardstick, is casting a shadow of length of a length of 4 feet. So all we need to do is simply relate the given information to to the best trigonometric function we can think of as well. So in this case, we are given this triangle for which this is the acute angle theta that it wants us to find, and we're given the length of the opposite side to the angle and the length of the the adjacent side. Which trigonometric functions relates those two sides? Tangent. So how about we go about tangent theta? That's 3 over 4, and theta is simply the inverse tangent or arctangent of 3 over 4. And well, of course, since 3 over 4 is not a number in the the unit circle. In fact, this would be a circle of a different radii, not of a different radius, not the unit circle. So let's use the calculator to compute this. And well, just make sure that you are in the correct mode on your graphing calculator in order to calculate this. So let me clear all this. Let me double check my mode. Oh no, it's in radian mode. Degree, second width, second tangent to evaluate the inverse tangent function, and this is 3 divided by 4. Close parentheses, click enter, and that should give us the desired angle. That's 38.86, 38.9 degrees. So does it say how many decimal places? Oh, the tenth of a degree. So that's 1 decimal place, 36.9. 36.9. And use the degree symbol because they want us to find degrees. Question?
I'm sorry, can you just go to the last problem real quick?
Yes. This one?
Yeah. Where did you get the divided by x? So tangent.
Oh, because tangent is that's opposite over adjacent. So the opposite is this radical right here, and the adjacent is x. All right. And this is the end of the section. Let's move on. Oh, so this is also the end of the chapter, by the way. Let's move on to a new chapter today. That's chapter 5. And well, chapter 5 is about trigonometric identities here. So here we're going to use more algebra than rather the unit circle that we have been using, or evaluating SOHCAHTOA thing, or points on a circle of radius r, whatever that radius is. So here we will finally do some algebraic manipulations. I guess it's I think it's, or at least in my opinion, the fun part of the trigonometry, right? So here is where we're going to put a lot of stuff together, not just knowing these basic identities. Well, those are identities that we have discussed many times. You know, the reciprocal identities, the fact that cosecant is 1 over sine, or sine is 1 over cosecant, secant is 1 over cosine, or vice versa, cosine is 1 over secant, etc. Quotient identities, tangent equals to sine over cosine in cotangent, which is the reciprocal cosine over sine. And the Pythagorean identities. And well, I think I showed you the trick to get these two identities already a couple of times, to get the sine, to get the tangent squared and the cotangent squared identity, and just instead of trying to memorize them, you can get them from sine squared plus cosine squared. The first one by dividing both sides by sine, and by sine squared, and the second one you get it by dividing this identity by sine squared. And the even and odd identities, just recall that because we're going to need them, recall that only the cosine and its reciprocal, which is secant, are even functions. That is, when we evaluate a trigonometric function at a negative angle, the negative sign disappears, as opposed to the odd functions for which we evaluate them at negative angles. The negative goes outside of the angle and becomes a coefficient of the trigonometric function. And we're going to need this for quite a bit, right? Well, so number one, we are going to start by simplifying trigonometric expressions. We're going to use a bunch of algebraic techniques to get that done. Number one, we might want to rewrite a trigonometric expression in terms of sine and cosine only. That technique always works. You know, for the most part, is the one that we're going to use. But of course, there will be exceptions in which, since there's no sine and cosine involved, well, there's no way to, or rather, there's no need to go to sines and cosines and then go back to the original type of function. So I'll show you in the different examples. A second technique that we have in order to simplify trigonometric expression to multiply by a ratio of 1, and mostly is what we call a trigonometric conjugate. We'll talk about it, how it looks like, how do we do, and how is it useful. Writing sums of trigonometric ratios as a single ratio. Well, that is like when we have a sum of terms divided by a quantity, like when we split up into many terms by dividing. And then what's next? The last one, factoring. And well, here we need to know pretty much all factoring techniques. The greatest common factor. What else? Factor by grouping. What else? Some difference of squares. Sums and difference of perfect cubes. Factoring trinomials. Every technique that you can think of that we can use in order to factor a polynomial, well, it's going to be useful here. You'll see how it works. All right, let's get some examples and simplify secant squared times cotangent times cosine. All right. Here I'm going to go with the first technique, which is to rewrite this trigonometric expression all in terms of sines and cosines. All right. So we know that the secant quantity, it's the same as saying 1 over cosine. Well, for example, these identities here also work for, okay, let me give an example. Secant squared theta, it's the same as 1 over cosine squared theta. All right? Or whatever power, or to the third power, or to the fourth power, or to the fifth power. Also, the angles may be different as well, like secant 5 theta equals 1 over cosine 5 theta. So these identities that you see here work for any angle, or a multiple angle, and they also work for every power as long as you do it on both sides. You don't have to do this, what I'm doing here, I'm doing this just so you can see how this actually works. All right. Well, so secant can be rewritten as its as its reciprocal, and that is cosine. That is the same as saying 1 over cosine squared x. And we know cotangent can be rewritten in terms of sine and cosine by using the quotient identity, the one that we have at the top. That is cotangent equals cosine over sine. Times, well, cosine is just cosine. So we're just going to leave cosine the way it is. Cosine theta. And I'm going to write it as cosine over 1, just so it looks like a ratio, like a fraction, like all the other functions. Yes?
Would you write cosine x and then...
Oh, yes. Let me change those to x's. Thank you. Because I was looking at the identities at the top. So, yep. So here's what's going to happen. Check this out. Cosine times cosine will become cosine squared when we multiply them. That is, these two factors of cosine will get divided out with cosine squared in the denominator. And that's just going to leave us with the following. That's simply 1 over sine. But 1 over sine, it's the same as cosecant x. Well, we need to be very careful here, because in some cases we may be required to leave our results in terms of sines and cosines only. So this is an okay answer. In some other cases, they may not want us to have trigonometric functions as ratios, but rather just like terms without denominators. That's what they want to do in some cases. Well, we need to be aware of the instructions in those situations. All right. So that's one example. Let's look at another example for which we can simplify this. Well, this one is going to take a good minute because, well, this is about combining fractions together. All right. So let's see. Okay. Back when we did something like 1/3 plus 2 over 7, well, we were not able to combine these fractions together because we didn't have a common denominator. Had we had both fractions with a denominator 3 or with a denominator 7, well, we can just go ahead and do the indicated operation in the numerators. However, when we have denominators different on both fractions, we need to come up with a least common denominator. That is, well, multiply numerator and denominator of the first fraction by the missing factor, which in this case is 7, and in this case multiply and divide by 3. This way we can create two new rational expressions, or rather rational equivalent rational numbers but with the same denominator, in a way that we can combine them together. That is 7 over 21 plus 5 over 21. And well, now that we have a common denominator, we can go ahead and combine them together. So this is 7 plus 5, that's 12 over 21. And well, it looks like we can still divide out because they're both divisible by 3, I believe. So 3 times 7 and 3 times 4. So that's 3 times 4. Oh, hold on. No, this is 6, not 5. My bad. So that's 13. All right? My bad. Well, so that's the fraction combined into one single together. Well, we're going to do the same here with trigonometric expression, that is 1 plus sine u over sine u. I'm going to leave a space for missing factors plus cotangent of u minus cosine u over cosine u. So in the same way that we multiply numerator and denominator of each fraction for the numerical example at the top, we're going to do the same here. That is multiply by cosine and multiply by sine. All right. Now that we have the same denominator, check how we have in the denominators of both fractions the same quantity, sine u, cosine u, sine u, cosine u. I know in the reverse order for the second fraction, but it's the same thing. 3 times 4 is 4 times 3 ultimately, right? So this is what we're going to do. I would like to put parentheses around this guy. Be careful. Put parentheses around this. Put parentheses around this. And I'm going to go like this. So this will be 1 plus sine u times cosine u plus cotangent u minus cosine u times sine u. The whole thing divided by sine u cosine u. All right. I know what you might be thinking. Maybe we could have done the distribution in the same step, but I'd rather write the whole thing first so you can see where the things are coming from. And then in the next step, yes, I'm going to distribute the cosine and distribute the sine here. That's going to lead us to the following rather. So that's 1 times cosine. That's a cosine. Sine times cosine is sine cosine. Well, these are unlike factors, sine. And then plus cotangent times sine, that's cotangent sine. And sine times sine times negative cosine, that's minus sine cosine. The whole thing divided by sine u cosine u. All right. At this point, we are like, oh, that's a lot of terms. However, notice how we can already do some simplifications, because we can tell already that we have a couple of terms having the same coefficient but opposite in sign. I'm talking about sine u cosine u minus sine u cosine u. And guys, whenever we're dealing with a monster like this, try to cancel out try to cancel out or combine like terms if applicable. That way you can start already simplifying the expression, because that's what it is about, simplifying an expression. Alright, so that's going to leave us with cosine u plus cotangent u sine u. The whole thing divided by sine u cosine u. Alright. And over here we could use the split up trick to write a couple of fractions together. I know we start what we started with and then go back to the same thing. Well, that's kind of weird. So that'll be, okay, cosine u, or you know what, never mind, I'm not gonna do that. There's a better plan, because if we split this into two fractions, that's going to leave us with a lot of terms. But otherwise, check this out. Let me highlight this cotangent here. Isn't that the cotangent function equal to the ratio between cosine? Isn't that cosine over sine? Okay, that sign in the denominator will divide out with that sign right here, leaving us with one factor of cosine that can be added together with this cosine to give us a 2 cosine instead. So we can do that instead. It will be a lot better. So that's a cosine u plus cosine u over sine u times sine u. So that's the quantity in the denominator divided by sine u. Looks like an n, and cosine. Okay, check this out. Let's divide out sine over sine, and that's cosine u plus cosine u equals to sine u cosine u. That'll add up to 2 cosines in the numerator, and in the denominator that's a sine u cosine u. Now, this looks already a lot better than actually having to split up the two fractions together. Otherwise, it would have been like a lot of work, and in fact, I claim that if we did it the other way around, we would have come back to the original problem. So, and all the effort that we did to find the least common denominator and multiplying the fraction by the missing, each fraction by the missing factor, numerator and denominator, would be worthless. Now, check how the cosines get cancelled. And that's going to leave us with 2 over sine, which is equal to 2 cosecant u. And that's the simplest that it can get, right? Where are we going to apply this? Well, again, we will also apply this in calculus. So most of the times when for those of you who have already taken calculus in high school, well, I think you know what I'm talking about. Actually, the calculus part, once you get there, you will find out that the calculus part is the easiest part. It's the changing one thing for another one, doing a really simple operation, but the rest of the problem is either doing some algebraic manipulations or trigonometric manipulations. And I'm talking about this kind of trigonometric manipulations in order to get simpler expressions, because for the most part we're going to use these trigonometric functions for applications, and well, you may not want to work with a huge expression to do whatever, finding a value related to certain context. Now you rather be more efficient and work with a more simplified trigonometric function, like in this case this one right here. Yes.
So we manipulated cotangent, so cancel out.
Which cotangent?
C.
This one?
Yeah.
So we turn cotangent into cosine over sine by the identity. Let me highlight it. And then that's to divide out the sines and to combine the two cosines that we were left with. Right? Let's look at another example. Simplify cosine theta over 1 plus sine theta. Alright. This one would be, I'm not gonna lie, this one could be a little tricky. And well, don't write this down first. So let's see. True or false? Is this correct? We can't do this, right? Unless we had it the other way around. 1 plus sine theta over cosine. That is correct. In this case, we can do it. That's 1 over cosine plus sine over cosine. But not in this case. We can't do this. And well, in this case, we can split it and use identities. That's a secant. And sine over cosine, that's a tangent. All right? As easy as that on the other case. However, not in this case. All right, how do we go about this one then if we cannot do this? I mean, it looks like the first thing we could do. It doesn't look like there's anything else that we can do. Well, in the previous page, we talked about the different techniques to simplify trigonometric expressions. Well, we already did changing in terms of sines and cosines, multiplying by missing factors to get least common denominators. And there's another technique to multiply by 1, you know, by a ratio that is equivalent to 1. You know, because if we multiply by 1, any quantity by 1, the quantity doesn't get, the value of the quantity doesn't get changed. And there's many ways to multiply by 1. For example, we can multiply by x, divide by x. Well, but that's not going to be useful. We can multiply by, I don't know, ln of x over ln of x. But that's not going to be useful either. So in this case, we are going to multiply by a ratio that yields a 1 that is useful to at least get to the first step. And well, on the techniques, the description on the first page, on the previous page, right? Well, it's the first page. I mentioned something about trigonometric conjugates. So what are those conjugates? We're going to talk about the denominator, and we are going to find the conjugate of the denominator. The conjugate of the denominator will be exactly the same quantity. So I'm going to multiply by 1 sine 1 sine. However, the conjugate will have the sign in the middle to be the opposite. Okay? And I'm going to put parentheses around this guy at the same time. You'll see why am I doing that. Alright. Well, what's the purpose of multiplying this by a conjugate? Because check this out. And I know what you might be thinking. Yes, we're going to distribute the cosine times 1, cosine times sine. That's going to give us cosine times 1, which is cosine theta, minus sine theta, cosine theta. Right? So the numerator, it's very straightforward here to keep going. Now, for the denominator, I know what you might be thinking. You might want to FOIL 1 times 1, 1 times negative sine, sine times 1, sine times negative sine. That's fine if that works for you. However, I feel like that's a lot of writing. But if you can recognize the forms, I think it's going to be a lot shorter for you to get through this. And well, how are you expecting to do this? Well, however you feel more comfortable with. FOIL the whole thing or recognize the pattern. What's the pattern that we can recognize here? Did you see this? A plus b times a minus b, which in this case it's the factor form of a difference of squares. That is some kind of, that's going to give us something squared minus another something squared. And those somethings are going to be 1 squared minus sine squared. Alright? Okay, what is 1 squared? Well, 1 squared is, come on, that's just 1. So So that's cosine theta minus sine theta cosine theta divided by 1 minus sine squared. Alright, here is where knowing how to manipulate the basic identities it's going to kick in. Okay, so check this out. Let's go back to the identities here. From this identity, sine squared plus cosine squared equals to 1. We can obtain two more identities. Number one, we can obtain the identity if I move the sine squared to the other side, I can get cosine squared equals to 1 minus sine squared theta. On the other hand, if we solve for sine squared, if I move the cosine squared to the other side, I can get sine squared equals to 1 minus cosine squared theta. So you don't have to memorize three identities again. Just knowing the basic Pythagorean identity, just keep in mind that from there you can move one term to the other side and come up with new identities. So we're going to use this idea to simplify this term right here, or to rewrite rather. So 1 minus sine squared, that equals to cosine squared theta. And this is by manipulating the Pythagorean identity. So let's write that down on the following step. And that is, what's that? Cosine theta minus sine theta cosine theta. That equals to cosine squared theta. And I think we can already see where are we going, because we can see that the numerator has a common factor of cosine that we can factor out. Cosine theta times 1 minus sine theta. Divide that by cosine squared theta and see how we can divide out 1 power of cosine. The 1 in the denominator gets cancelled with 1 of the 2 powers of cosine from the denominator. And then from here we're left with 1 minus sine theta over cosine theta. So, number one, we need to be aware of the instructions here. If we were asked to just simplify that expression and leave it in terms of sines and cosines, well, then this is a good final answer. But otherwise, if we are required to leave this result in terms so that no trigonometric functions are left in denominator, then we need to go the extra mile, and that's what I'm about to do. Here we can do the split up trick that we did before, right? What I did here, and that's 1 over cosine minus sine over cosine. And then keep using basic identities to rewrite this too. We know that 1 over cosine, or cosine is the reciprocal of the secant function, that's secant theta, and minus the ratio sine over cosine, that's a tangent function. So I'm going to box the two results just in case, just so you can see which one that both are okay results, but that's going to be again based on the instructions. Do you want a result only in terms of sines and cosines, or do you want to simplify it all the way so that you don't have any trigonometric functions in denominators? And that's the equivalent expression. Yes?
If we see something on the test, how would you want it to be written?
It would be on the instructions. So it would be on the instructions on the exam. Yep. Let's see. Let's look at another example. Simplify sine squared v minus 1 divided by tangent v sine v minus tangent v. And I know what you might be thinking. Divide or rewrite that tangent in terms of sines and cosine. But just think about it. That's going to give us a madness here that is a complex fraction, and we may not want that. All right. So how about, check this out, how about the denominator? Do you observe anything interesting in the denominator? Or actually on both the numerator and the denominator? And if so, what is that? What do you observe? Any ideas? What would be a good first step? All right, I'll do it, I guess. Well, the numerator looks like something squared minus something squared. All right. So that means we can use the difference of squares factoring technique to factor the numerator. Sine v plus 1 sine v minus 1. And then notice how we have a tangent as a common factor in the denominator that we can factor out. Tangent v times sine v minus 1. And notice how we can divide out the sine v's. And we're going to be left with sine v plus 1, the whole thing divided by tangent v. All right. We are essentially done, but in this case, number one, we don't have everything in terms of only sines and cosines, and also we have fractions together. So we're going to split the fraction, that is sine v over tangent v plus 1 over tangent v. And well, I'm going to move these tangents to the numerator as a cotangent. So cotangent v, because cotangent is the reciprocal of tangent, and tangent is also the reciprocal of cotangent. And then multiply that by sine v. Sine v, and 1 over tangent, that's a cotangent also. Well, that cotangent in the first term, well, that's the same as saying cosine over sine. Then let me highlight it so you can see where is this coming from. So this cotangent here will be the ratio cosine over sine, and that times sine. And check how we can divide this out. And this is simply, I'm gonna leave this one as a simply cotangent. Because even if we rewrite that cotangent as a cosine over sine, that's not going to reduce anything at all. However, it can reduce these two signs, and that's going to be cosine v plus cotangent v. And that's final answer for this one. Let's see if we can do anything else. No, I don't think we can do anything else. I mean, I feel like if we write this cotangent as cosine over sine and then factor out the cosine, it's like going in circles, you know? Well, cosine v plus cosine over sine. That's another way. Factor out the cosine. That's 1 plus 1 over sine. And this is also cosine v, 1 plus cosecant v. Well, it's not necessarily going in circles, because, and I'm glad I'm doing this, because later in calculus, when you're applying this, you may need to rewrite that expression maybe in terms of cosines and cotangents, or maybe in terms of cosines and cosecants, so we can divide out other factors or put it together with other kinds of expressions, equations. So it's good to practice with the different ways to go about these identities and explore the different possibilities here. All right, let's see. Let's do one more. Okay, establishing identities. Well, the idea of establishing an identity, it's to show that those statements are true statements by pretty much working on the hardest side of the expression or the statement, and make sure that this is equivalent to the expression on the right hand side. So most of the times, again, it's the left hand side will be the most complicated side. We're going to work our way through that in a way that we can get to see, in this case, the right hand side. So let's work on the right hand side for the first expression. Okay, I mean this for the first equation or identity. So sine theta times cotangent theta plus tangent theta, we can distribute the sign to get sine theta times cotangent theta. Distribute and distribute and distribute over the tangent term plus sine theta tangent theta, and then from here how about we write down those cotangents and tangents in terms of sines and cosines and see what we get. All right, let's see. So that's going to be sine theta. Cotangent is the same as saying cosine theta over sine theta plus sine theta times tangent, which is sine over cosine theta. Let's see what we get by rewriting everything in terms of sines and cosines. All right, so notice we can actually divide out sine over sine to get the quantity cosine theta plus, I'm going to leave a space for something, you'll see, plus the quantity, okay, sine times sine, that's a sine squared theta, and divide that by cosine theta. What do we have here? Check this out. This cosine theta is the same as saying cosine theta over 1. Now we are in the need of combining two fractions together, but these two fractions do not have the same denominator here. So we need to find a common denominator, again, by multiplying the fractions by the missing factors. Well, it turns out that only the first term requires to be multiplied, numerator and denominator, by cosine theta, not the second term. The second term can be left as is, and well, so this will be cosine squared, that's a cosine squared theta over cosine plus sine squared theta over cosine theta. And that equals to combining fractions together, write it in one single fraction, cosine theta, that's the new denominator, and that's cosine theta squared plus sine theta squared. And we can simplify the numerator because it turns out that the numerator, cosine squared plus sine squared, it's actually an identity. Let me highlight it. That's cosine over cosine squared plus sine squared, and that's an identity that's the identity that equals to 1 over cosine theta. And furthermore, we know that 1 over cosine theta equals to secant theta. Isn't that the right hand side of the statement here, of the identity that we wanted to verify? Alright, so that's what it is about. So we are going to prove identity, well, not necessarily prove, but rather verify identities. So use all these tools called basic trigonometric identities, reciprocals, quotients, and Pythagorean, and also the even and odd properties to go about verifying these identities. All right.